Hello. This video is going to be about the start of chapter 12 on similarity. And I'll warn you, there are some definitions at the beginning that might feel very technical, but once you wrap your head around the ideas behind similarity and proportionality, a lot of it feels clear. This word proportionality has a very specific definition, but I want you to be able to think about it a few different ways, and that makes it much easier. So this word similar, the general idea is that geometric figures are similar if they have the same shape, but not necessarily, pardon me, not necessarily the same size. So maybe I have a large square, so four right angles, four congruent sides, and maybe I have a smaller square. So in terms of their shape, they're exactly the same, but obviously one is bigger than the other. This would be an example of similar figures. I would say any two circles are similar. Triangles can be similar if they have the same shape. And by shape, I mean something much more specific than it is a triangle. But for example, if I have a right triangle like so, whose sides are 6 and 8 and 10, and then I have sort of the version that's half as big, whose sides are 3 and 4 and 5, we might feel that this is similar. Right? It's just the shrunk down version, but it's the same shape in a very specific way, not just, oh, it's also a triangle. We'll give a more technical definition as we move forward. So when we have similar figures, the corresponding angles will be congruent. Again, this isn't really the definition yet, but that's the idea. Corresponding lengths might not be congruent, but when we look at the ratios, we see they're the same, and that's called proportionality. So for example, in these blue triangles on the right, 6 and 3, that's a 2-to-1 ratio. 8 and 4, that's a 2-to-1 ratio. 10 and 5, that's a 2-to-1 ratio. In every aspect that we can measure, the triangle over here is double the triangle over here in all of the lengths, not area, but in lengths. We call that idea proportionality. And I'm going to give you the formal definition of proportionality, but really, if you just understand that there's this ratio that's always the same, that's the gist of it. So if I have two sequences, and a sequence is just a list, so I have one list that starts A, B, C, and maybe it keeps going, and I have another list, P, Q, R, that keeps going. So if we have the case that the ratio of first one to first one, A divided by P, is equal to the ratio of second one to second one, B over Q, and that's equal to the ratio of the third one over the third one, C over R. As we go down, if the ratios between corresponding elements in those sequences, so this is basically saying ratios between corresponding terms, right? They have to be corresponding. They have to show up in the same part of the list, are always the same. Then we call those sequences proportional. That's our definition of what proportional actually means. It means I have two different lists, and when I pair things up, the fractions are always the same. Maybe, oh, we always have something that's twice as big as the other number, or we always have something that's 1/5 as big as the other number. Sometimes it's written this way with this squiggle in between. I'm not going to do that, but you may see that in the future. Right, so just as an example, if I have one sequence that begins 1, 3, 5, 4, 2, let's just say it's those five numbers. And then I have another one, 5, 15, 25, 20, 10. These are proportional sequences. And why is that? Well, 1 over 5 is 1/5. 3 over 15 reduces to 1/5. 5 over 25 reduces to 1/5. The ratio is always the same. If you want to express this using multiplication, if you want to say, oh, we just took all the numbers and multiplied by 5, that's another way of looking at it. It's basically the same fact. When I pair these up, I'm always doing the same thing from the point of view of multiplication and division to explain how the top number is related to the bottom number. And there's just a quick theorem here that says proportionality between sequences is an equivalence relation. And I'll remind you that means it's symmetric. So if list A is proportional to list B, then certainly list B is proportional to list A. I could have switched the order up here. It's reflexive, meaning that a list is proportional to itself. There's always a 1-to-1 ratio. And it's transitive. So if list A matches list B and list B matches list C through proportionality, then list A would match list C. Now, the really key thing is once we have a relationship of proportionality, we can rearrange that to find other equal fractions. So proportionality can be expressed in a lot of different ways. That's what I want you to kind of get out of this. And let me give you an example, and I'm not going to use letters here, I'm going to use specific numbers. Having a picture in mind will make this much easier. So here's what I'm going to do. I'm going to draw a segment like so, that's broken up, say like so, and let's suppose this is 1 and this is 3. And then let's suppose down here, I have something that's twice as long. That didn't quite work. So this distance is 2, and this distance is 6. So we might see proportionality here. 1 compared to 2 is the same as 3 compared to 6. Using the proportionality symbol, the sequence 1, 3 is proportional to the sequence 2, 6. But I want you to realize there are lots of ways of expressing what's going on. So for example, I could say 1 over 3. So let's think about where are the numbers 1 and 3 coming from? 1 over 3 is left compared to right on the top. So this is left over right. Left over right measured in one place, if we truly have proportionality, should be the same as left over right measured in another place. Left over right measured in the bottom would be 2 over 6. And yes, that's true. 1 over 3 is the same as 2 over 6. Or what if I said 3 over 1 plus 3? Where's that coming from? 3 over 1 plus 3 from the top is the right over the total of left plus right. Up here, the way right compares to the total of left plus right, if we have true proportionality, should be the same as how it works here. Down here, what is right compared to the total? Down here, right compared to the total is that. And those are equal. 3 over 4 is equal to 6 over 8. Or let's just look at some other ways of doing this. 2 over 1. 2 over 1 is bottom over top on the left. I'm looking at the two numbers on the left. Bottom over top is 2 over 1. Well, how else could I compute bottom over top? Bottom over top on the right would be these two. These are the two things on the right. The bottom one is 6 and the top one is 3. And those are in fact equal. So when you have proportionality, there are a lot of different possibilities for which fractions are equal. You just need to match them consistently. Hopefully you have a picture in mind where there's a logical way of understanding which things match which things. Right? In this example, there does the one match the two in some logical way? Yeah, they're both on the left. Does the one match the three in some logical way? Yeah, they're both on the top. Does the one match the six? Not really. So what you'll notice is in these different equations I've set up, I never have 1 and 6 directly compared to each other on the same side of the equation because they're really not related. But there are a lot of different relations. Right compared to left, bottom compared to top, left compared to total of left and right, top compared to total of top and bottom. There are a bunch of ways to express this, and you'll always get equal fractions given that we had some version of proportionality in the first place. So when I say that things are proportional, don't get hung up on specifically which fractions are equal. When we have proportionality, there are lots of equations with fractions that will express it. And often in doing a problem, one of them will seem more obvious, or maybe one of them is just the first one that occurs to you. There are a lot of ways to use this once we start using it to solve problems. All right, now section 12.2 is about similarities between triangles. So I'm going to give you the definition, not of all similarity, but of similarities for triangles. So given a correspondence between two triangles, if corresponding angles are congruent, so that's part of our definition, and corresponding sides are in proportion, then we call that relation similarity and the triangles are similar. So let me draw an example for you. Maybe I have a triangle like so. Let's make this one kind of small. And then I have a bigger version, but that appears to be generally the same size and shape. Now I'm going to draw them with similar orientation just so it's more obvious to see what's going on. Right, so the black one is certainly bigger, not quite twice as big. And let's suppose we have, here's ABC, right, here's DEF. So similarity, remember congruent triangles means all the angles are congruent and all the sides are congruent, so it's really 6 facts. With similar triangles, it's more like 4 facts. So here's the idea. Angle A is congruent to angle D. Angle B is congruent to angle E. Angle C is congruent to angle F. And the sides are in proportion based upon this correspondence. Now I can't really mark that in the diagram, but I'm just going to draw dots to keep track of things. So A matches D and B matches E. So AB matches DE. I don't mean to say they're congruent, but they match in some meaningful way. So the ratio of AB to DE would be the same as the ratio of these corresponding sides on the upper right, AC to DF. And that would also be the same as the ratio between the bottoms. So this is really all one fact, that those 3 fractions are all equal to each other. The angles measures are exactly the same, and the lengths are probably different, but they have this correspondence where the ratio is always the same. If AB to DE means I have to multiply by 1.5, then all of them mean I have to multiply by 1.5. If all of those things are true, these 4 facts, that's the same as saying triangle ABC is similar to triangle DEF. And I will remind you, as was the case with congruent triangles, the order matters. The order in which I write the vertices of those triangles has to match up in the way that makes sense of the similarity. So half of this is very similar to what we did with congruent triangles. The other part, we have this proportionality. And remember, proportionality maybe can be expressed in different ways, but this is one way of expressing it. So this section was actually very short. It just shows you the definition. And quite soon you'll be doing some practice with this in class to, start breaking this down and figuring out, what can I do with this? Just as a quick example though, right? Suppose I had a triangle like so, and this is x, y, z, and suppose here is triangle. I'll actually draw it this way. Here is triangle DEF. And suppose that I tell you that triangle XYZ is similar to triangle DEF. And maybe I tell you that this is 8 and this is 9 and this is 4. And suppose that I tell you that this over here is 6. And I want to find x and y. So just as a quick example of what similarity does for us, we know that if these triangles are truly in proportion, right, if they're truly similar, then the sides are in proportion. So I'll just write down what that means. Segment XY matches segment DE. So 4 over y is a relevant fraction. Segment YZ matches segment EF, right? Maybe that looks right from the picture, but you can also read it off. YZ matches EF, which means that 9 corresponds to x. And then finally, XZ matches DF, which means 8 corresponds to 6, and these are all equal. If they're all equal, I can write them in any order. So if I wanted to find x, I could say 9 over x equals 8 over 6. When fractions are equal, cross multiplication is your friend. So 8 times x equals 9 times 6, which is 54. So 8x equals 54, and x is 54 divided by 8, which is 27 over 4, which is 6 and a quarter. Nope, sorry, that's not 6 and a quarter. That is 6 and 3/4. To find y, we could say 4 over y is equal to 8 over 6. Cross multiply, 8 times y equals 4 times 6, which is 24, and y is equal to 3. Let me just look at this. For some reason, I feel like I've made a mistake here, but maybe not. No, this looks right. Sorry about that. So this is just a little taste of what we can do with similarity. Once we know similarity, we know what kinds of things are the same. The angle measures are literally the same. And the sides are not the same, but the ratios between the sides are the same. So hopefully we have enough information where once we write out all of the fractions that are equal, somehow we have a relationship that we can solve for. Because when I write this, I'm really writing 3 different equations, and whichever one is helpful, right? I can say first is equal to second, first is equal to third, second is equal to third. So you have different options as to what to solve. Okay, but I've talked enough, and you will be practicing this in class.